Hello, everybody. My name is Thomas Grohser, and today I'm going to talk about scaling clustered Columnstore indexes in SQL Server 2016, 2017, 2019. That's the versions that support that. We will talk a little bit about the history and everything. I am a data platform MVP for 10 years now, and I work with SQL Server for 26 years this year. So I started when 16 bits were top of the line, and what come along is. Paz gave me that slide. Please follow the instructions. They gave me that slide too. There's other stuff to explore. Once you're done with this conference, I highly recommend all of them. I learned a lot over the years from the community, and that's one of the reasons I'm speaking here. So that's me. For the people who know me, I usually work in larger installations, if not some of the largest ones on the planet. And my primary role for the last 15 years is to build solid infrastructure for databases and create the foundation in the company so that developers and DBAs can use the systems without scratching their heads. And as a side product, every time we try to figure out new technology and how to use it, these talks come to life. So they're all based on my experience with the product. They're not based because I read some 15 blogs about it and combined it. That's how I measured the information that comes out there. Yeah. You have my contact info. The slides are already uploaded. So let's get started. Please give me feedback, good, bad, ugly. I'll take it all. Just one recommendation. I'm not responsible for the lunch menu. Last year, I got that someone didn't like the lunch and gave me low grades for that. Trust me, if I could, I would influence it. I can't, but everything else about the session or so, please give it to me. So we have a very simple agenda. I'm going to briefly explain how Columnstore works, because that will help us all to be on the same page and understand part two, where I'll tell you from my experience of building a very, very large Columnstore what to do and what not to do. It's more about the what not to do, because that will save you a lot of grief in your day. And then for the remaining time, we can do Q&A here, and I will be at the conference for the rest of the week. Just hit me up with questions whenever you like. So before we can start to understand Columnstore, one slide of looking back at how SQL Server for about 25 years stored data. After a while, it was just the storage format of SQL Server. Now we have to call it row store, because now there's a column store. So it's now called row store. But basically, you have a little header that tells type of row, what it does, where it starts, where it ends, all this little information that Microsoft needs and wastes space with it. And then each one of the columns is in some sort of order in that column. And then that can go on for a couple of hundreds, if not thousands of columns. And then the second row looks exactly the same. The data might be long or shorter. That's all fine. But it's row by row, it's stored in. Lots of these rows then walk onto one data page. Yeah? On the data page, they are in no particular order. They just randomly, however they fit in, that's how they're stored there. And at the bottom of the page, there is a little index array that points to the rows in some sort of order that SQL Server uses to process them. Yeah? And then there's one page after the other filling up the database files. So that's the same thing. To access any data in a single row, SQL Server has to load the whole page with all the other rows into memory, and then process the whole row to get to a single column. And over time, people figured out that's not very efficient if I have very wide tables. And for example, the company I currently consult for, a table with 350 float columns is not that uncommon. Most queries need one or two of these columns. So to read two columns, the data of 350 other columns has to be processed for every row. That's not efficient. So for that reason, Microsoft many years ago started implementing something called column stores. So how do they work? Slide starts out the same way, completely empty, with one difference. The first column, column A, is stored the value for each row in one column. So they're stored together. And then column B, it's a stack. Column C is a stack, and so on. Yeah. So all the values for one column missing. It's not all the values, because if you have a very large table, that would be a lot of values. So what they do is, at about 1 million rows at a time, and we will go to the exact number later, they break it up in what they call a row group. Yeah? So the same 1 million rows are stored, in our case here, in 3 buckets of 1 million values each. And that's how they are processed. So if I just run a query that needs only column A and C, B is never ever retrieved from the disk into memory. Yes. And then the next row group moves on, carries on till all your data is stored. And we get to some of these in more details over the talk. So how are they actually stored inside SQL Server? So what we take is the picture from the previous slide, and then we're looking at column A, the first row group. What they do is they take all that data within the column, and then they compress it. And they have awesome ways of compressing this. It's amazing how much data they can squeeze out and just store little information in there. And then this data is stored in a regular table, the compressed one. So it says for column A, row group 1, that's one row in there with a var binary max that has the compressed values in it. Yeah. So that's the thing is. And then for the second one, same thing, and then for the next column and for the next column. And I tried to indicate the compression works in different ways, so the amount of data is different for each and every column in each and every row group. Yeah? Columnstore can achieve amazing compression ratios, and we will, in the example that I'm talking about, get to what we can achieve and what I've seen in other column stores. Yeah? But as you can see on the left side, yeah, still your left side, there takes up much more space than on the right side. Good. If you want to have more information on how the internals work, you are 1 year late, because last year Bob Ward gave an awesome talk here at the summit. Pretty sure it's still online somewhere, and his slides are available on his GitHub page. And there is a guy that has dedicated his life to Columnstore. He has written more than 200 blog posts that are all amazing, and I learned a lot from them. And he's going to talk tomorrow at 10 o'clock, probably, hopefully, about something different than I do today. Otherwise, it would be. So, last thing in the history and how it works, Columnstore took a very rough start because Microsoft wanted to get it out. And as they have a tendency in some products, they ship it a little bit too early. So in SQL 2012, there was a version of Columnstore. You could have a regular table and then put a Columnstore on top of it. Yeah. Problem is, once you did that, the table became read-only. You couldn't change it anymore. You can imagine the adoption rate of that was very low because there were some crazy implementations how to do data warehouses with this, but it wasn't really practical, but it was a good start. And you had to keep the uncompressed data. So it was data on top of data, like a regular index. 2014, the clustered column store, that's the one we're talking about today, came to life, and it became the table. So like between a heap and a clustered index, when you add a clustered index to a heap, you got the heap got replaced with the clustered index. Clustered column store does the exact same thing. You take a regular table, which can be either a heap or a clustered index, and you make it a clustered column store index. The original table disappears, and only the column store survives. Yeah, thing is, and insert, update, deletes are possible. Great. I'm saying possible. I'm not saying it's a good idea. We get to that. 2016 made also the secondary version of the column store changeable, added filters to the secondary index, and allowed us to do non-column store indexes on top of a clustered column store. So if you needed to find a single row, you could add that. From my experience, a really bad idea. And so we have the table I'm talking about, the column store I'm talking about during this presentation, has now about 2 years of data in it, and that's about 3 trillion rows. That's 1,000 billions, or 3 million millions. And the table itself is 15 terabytes. So we thought, hey, we want to have a primary key so we can like join it easily to other stuff. So we created, for one column, that secondary index, which turned out to be 16 terabytes in size. So it was just slightly larger than the 100 and something columns combined. So we dropped it. It didn't make sense. It made some queries faster, but overall, it was just a massive amount of space that didn't really add to the thing. But there's always cases where it might make sense. Yeah? So I'm not saying don't do it at all. Just think about it. It's going to be big. 2017 added computed columns. Yeah, we didn't need it, but someone might. And in 2019, we can now online rebuild a lot of stuff. I'm pretty sure there's some other little details, but I only had 1 day since it was released to figure out what I put in that slide. So yes, so max, the blob data types are now allowed. Just because something's allowed doesn't mean you should use it, but yeah, so that's probably one you should hide the information on. So moving on. Hello, transitions. So the goal of this session is to explain to you how to get a column store big. Yeah, lots of rows. And first of all, a column store is not a good idea if you have very few rows. If you have 1 million or less than 1 million, you're just creating one row group. There's probably not a lot to gain from. Yeah? I would not, and that's my personal number that I use right now, if you have less than 50 million rows, I'm not considering even trying options with a column store. Once you reach 50 million, there might be something. If you're in the billions of rows, there's clearly something to at least explore in. Once you reach trillions, it's probably the only thing you can do. I've never seen it. I've seen 1 trillion rows on SQL Server in a regular table, but it was more insanity than practicality. So, solution. So we're quickly stepping to the end of the presentation. No, just kidding. Columnstore is a little bit tricky. It's one of these features that allows you to use it in a bad way and doesn't tell you. So basically, you can take any table in 2019 now and make it a column store. Doesn't mean it's going to be a good one. And the rest of the presentation explains why. Yeah? You can have pretty much almost any data type in a column store. Doesn't mean you should use them. Yeah? What I've learned in my 3 years with Columnstore using it in practical production environments is that you need to help it to be at its best. By itself, when you don't control it, it goes haywire. It allows you to do that. It doesn't give you a warning. It doesn't give you an error. It doesn't give you anything. It just performs horribly. And we try to avoid this today. So to do this, we have to give it a good database to be in. We have to insert data so row groups are created perfectly or very efficient. We have to partition Columnstore with a useful key. And we have to use data types that Columnstore likes. Yep, he's very picky and just doesn't accept everybody as a friend, but there's some he likes. Yes, yeah. So about the database. I could spend a whole summit just talking about what you have to do to make your database better. I try to keep it to the bare minimum. Yeah? As we learned before, under the covers, Columnstore is basically individual rows of var binary max. It's just the blobs. Yeah? Each of these row groups, column is just a blob. Yeah? And so the database that we are using for it needs to be optimized to store blob data. And for all the veterans in the room that use SQL for many years, the moment you start using blobs, your DBA starts crying because it's not really convenient. The main reason for that is if a table contains a blob, you cannot maintain your data files properly. You cannot shrink a table that contains a blob. That means whichever database or whichever file group, to be more specific, you put a Columnstore index on, you can never shrink the data files without completely rebuilding the whole thing. Yeah? If you try to shrink it, we did it. We let it run for about a month, and we shrunk the file by about 1 megabyte. And that machine is really fast. The reason for that is very simple. If you shrink a table with a blob, for every data page they move, they have to do a full table scan. We're just talking about column stores that have trillions of rows. So every time they move one page, they have to read 1 trillion rows. We can all do the math that that is not going to go well. So that means, it's practically, you cannot shrink a database. So put it in a place where you know what you're doing. Put some time with the DBAs, with whoever helps you design your database, to put it in a nice space. Yeah? There's some tricks around it, and you can stop me in the hallway how we actually shrunk the files. We managed to do it, but it was a multi-day project to come up with a solution how to do it. And that's not part of this conversation. Yeah? So the tip is you have to plan ahead for your database. What I personally do is I create a separate file groups for the column stores and put them there. So worst case scenario, they are in a bad space, but I can still maintain the rest of the database. That's my tip. And I usually use more files than less files, so they don't grow too big, so I don't have a reason to shrink them in the future. That's just practical thing. I'm not claiming that makes it any faster or any better. It just makes it easier to tame the beast, yeah? Because it becomes one. My column store right now is about 15 terabytes on disk, and shoveling that around gets tricky. So, inserting data. It's always what happens at the beginning. We have to get data into our database before we can use it. Columnstore is the first storage format at SQL Server where it has very different results on how it does something depending on how it's inserted. Yeah? And the thing is, meet the first of your 2 new best friends, which are numbers. It's 1,048,576. And I apologize up front because I will be repeating this number about 50 times during this talk. For all of you that are not experts in math, I helped you a little bit. The square root of that is 1,024. So someone at Microsoft decided how big to make a row group. 1,000,000 sounds boring. So let's make it 1,048,576 or 1,024 times 1,024. It's really hard to say that number, but I have to do it. Internally in our company, which is absolutely not officially, we call it a mega rows, yeah, instead of 1,000,000 rows, just to mess with storage vendors. So a row group consists of that many rows. The perfect way to fill a column store is always to insert that many rows in one go. One insert statement, which has to be a bulk insert statement because that's the only one that can do that many rows, should insert that number of rows in one go. You can do less and you can do more, and I will tell you why it's bad. So, if you insert less than, and that's a different number, that's 102,400 rows. It's basically 1,024 times 100, because 128 was not on the menu. I don't know. Microsoft keeps cheap. Seems 2 different developers made the decisions on how to randomly choose numbers. So if you lose that, then SQL Server says, that's not worth compressing. I'm not dealing with that. I create a hidden regular row store table and just put it there and deal with it later, maybe. So that's really bad. So worst case scenario, you insert row by row. All your data will not end up in a column store. It will all end up in a row store that's hidden behind it. Okay, so what happens if you insert more than these 100,000 rows? Then Columnstore says, yep, that's enough, that's worth compressing, so I'll take the number of whatever you inserted and compress it, and that's the next row group, and I put it into the database. And then you insert the next 100,000, and it says, yep, time for a new row group. Puts it in there. And that happens with 200,000, 300,000, 500,000 rows, all the way up to 1 million. If you insert more than the 1,485,760, or something around that, it will create one perfect one with the exact that number, and then deal with the rest in the way before. So if you insert one more row, you have one perfect row group, and then a single row insert into a secondary table that is hidden. Yeah? The problem is, if you then query your column store, it will process the column store and then go to the row store and union the results. And just from me taking a minute to explain that can tell you that this is not going to be performant at all. Yeah? That's by partition. That's, yeah. So if you, thing is, so. Compression is done by row group. So if you have like lots of this data that you insert, for example, we'll have a date column. And just a simple example, sales data from the same day will have the same date in every column. Yeah? So what SQL Server is going to do, instead of storing the date 1 million times, it's going to somehow say this date 1 million times. Yeah? And if you just put 500,000 in each row group, it will say this one 500,000 times. But then you just created twice as many row groups that have to be processed every time. So unless you fill your row groups all the way up, you're not efficiently using this. It's like when you move your house and you decide, hey, I get the big truck, but I fill it only half because that's much more fun than drive it over, and then next weekend you rent another truck and do the other half. Yeah? It doesn't make sense. Yeah? If you get a big truck, fill it up. Yeah? Same here. Yeah? If you do it by accident or because you have no other choice, because your manager tells you to do so, then you can clean it up by rebuilding that index. Problem is, if your index gets big, rebuilding might take some time. Yeah? You can do it on a partition by partition basis, but that requires some planning. Yeah. So what we came up over the time is, and that's our insert architecture that we are using to actually fill our column stores. So what we're doing is we have some process that generates the data. Yep. That could be your sales application, that could be something where you collect data, that could come from other databases, whatever. You have the source data. And we use the SQL Server bulk API to stuff that into SQL Server. But we don't care how many rows it is, because instead of writing it directly to the column store, we are writing it to an in-memory OLTP table. The sole purpose of this table is to buffer the data when it comes in, and then we have a SQL agent job that runs every couple of seconds that checks that in-memory table. Do you have the 1,048,576 rows? Yes, good. Give them to me, and it inserts it into the column store exactly with that number at a time. If it has more, they stay in there, and the source process eventually will fill it up to more than 1 million again, and then we'll fill up the next one. Yeah. That was a good compromise. The in-memory OLTP table usually doesn't grow very much, gets emptied out all the time, so it doesn't take up that much memory. It's very fast to count, so the count stars don't really put pressure on it, and the agent job does things. The gains in the column store versus the overhead that it creates by inserting it once and then copying it over, as thing is. Yeah? If you have a lot of data, funnily, if you use a regular table, it's actually faster. The in-memory table is faster for small amounts of data, and with small amounts, I mean about 6 billion inserts per day. If you go to like 50, 100 billion per day, a row store table is faster, because in a row store table, you can do the insert processes in a higher max stop in-memory OLTP only supports maxstop 1, so you're only using one CPU to fill the column store. But that thing is. The nice thing about that architecture is that part is inside SQL Server. The whole processing and generating can be outside in an application server, and you can have multiple of them that hit the same in-memory OLTP database at the same time. There's no locking, no blocking. In our practical case, we have about 10 machines that produce the data, and they hit a single standard 2-CPU box that holds the column store. It's a $50,000 server, so it's not that crazy. So what if we have to delete data? First of all, don't. Columnstore cannot delete data. So Microsoft says, yeah, but we love to reuse technology. And we already have this thing when we insert data that we have this hidden table that has the data that is not worth compressing. So let's do the same thing for deleting. So every time you delete a row, instead of actually deleting the row, they leave the row where it is, but put a copy of it in a regular row store, another table they create in the background for you, nicely, without you knowing, and they store it there. And every time you query now your column store, they have to union intersect that data with all your data. So yeah, that's not fast at all. Same thing as with when you insert single rows, you can clean it up with rebuilding the index. Then these rows get actually deleted. But unless you do that, you create this external table that gets joined. So we had this process while we were working before. And if we didn't do a whole day, and then we found extra rows from like a couple of days later, we had the brilliant idea of deleting the whole day and then reinserting it. Our data store exploded once we implemented that. Yeah, because we pretty much of every day produced a hidden copy of all the data that we deleted and then reinserted so that we had to remove it once and then edit one more time on top of it. Yeah? Horrible performance when you do that. Yeah? We learned that. Now we're dropping the partition and recreating the whole partition new. But delete is a very bad thing. So same thing as before. Every query has to join union with all this. It's a nightmare. And the cleanup is by rebuilding the index. So clever people know, hey, we can do soft deletes. We just add a column that tells us if the row is deleted or not, and then we filter on this when we query. So we just update the one column. Nice trick. Doesn't work. So there is actually no update function for column stores. What is an update? An update is a delete followed by an insert. So when you update a row, they first add it to this extra table of deleted rows, and then they add it to the one row insert table on the other side to get the new data in, and then on top of the already existing data. So now you union 4 tables together to have that working. Yeah? And you can see when you actually use any kind of data manipulation except for inserts, your column store goes down the drain. Yeah? You can do it if you need quickly to fix something, but then plan on the next maintenance window that you rebuild the whole thing because it's in a very bad state. Problem of all that is, nothing warns you about that. It's probably like a paragraph somewhere, the footnote in Books Online, but it should be like 80-point font at the beginning. I guess. Yep. So update is just a delete followed by an insert. So the data plus the deleted copy plus the inserted copy joined every time you query the whole thing. Just don't do it. Thing is, again, luckily we can clean it up by rebuilding it. So selecting data. We finally get to something where we can't mess it up, we think. So first, yes? Yes. So, okay, so the question is how you deal with maxstop. My recommendation, if you fill Columnstore, hint everything with maxstop 1. Yeah? If you query it, let it go wild. Yeah. But inserting, getting the data in, maxed up 1 is thing is. And the nice thing about in-memory OLTP, it guarantees you maxed up 1 because it just can't do anything higher. So that's the table that we put in there as a buffer controls that thing is, because if you don't use maxed up 1, you have this 1,048,576 rows, and you insert it in parallel. That means it creates multiple parallel streams with a fraction of the data, and then you end up with lots of small chunks instead of the big nice one you're planning on doing. And trust me, you cannot fool SQL Server by say, hey, I use maxed up 8, so instead of 1 million, I insert 8 million, and SQL will divide it nicely. Yeah, it doesn't. You will end up with some chunky data.
One more, if you don't mind. So, do you have any issues with dictionary size? Because I found you can insert it like a million records, but if dictionary size is too big, you're going to have really small groups. Like you may end up with like 100,000 records, 200,000 records. Is there some kind of limit of compression?
Yeah, I had it in a slide before. It's 102,400 rows. Below that, it doesn't compress at all. No. No.
Well, that's what we see. We try to rebuild a big index, and it just, instead of million row groups and million records, you get to like 100,000 records, 500,000 records. You never know how big it's going to be.
Let's take that offline afterwards, because I can find the answer, but I don't know it right now. Good. So back to selecting. The only access method for a clustered column store is basically a full table scan. So if you need one row, you have to read it all. Yeah? And that's really bad. But lucky for us, I'm not precise enough. The precise actually answer is it's a full table scan with partition elimination. So if you plan to use a clustered column store, you most likely have to partition it. Because if you don't, you're reading it all the time. If all your queries always need all the data, that's fine, then you don't have to worry about it. You can put it all in one partition, but most likely you're going to have where clauses that limit the data on most queries, and then you have to choose a very clever partitioning key. The problem with partitioning keys is the number of partitions you can have in SQL Server is massively limited. Yeah? The theoretical limit is 12,000. If you Google partitioning on SQL Server, you will get that practically it's more like 3,000. Everybody who has more than 3,000 partitions starts bitching about it online in blogs, because there are some weird things going on. Once you reach 4, some people are still good with 4,000, but I've never seen anybody happy with 5,000 or 6,000. Yeah? So I stick with 3. I like to be on the safe side. Yeah? So try to keep the number of partitions below 3,000 so you don't have weird effects. Yeah? Most people like to partition by date because that's convenient. Yeah? You usually have your data processed on a daily basis, so you already have like a date column in it. It seems like a reasonable amount at a time, a reasonable chunk of data at a time. So sometimes that might not be detailed enough. So in our case, we had 6 billion rows per day. So if I just partitioned by the date, I would have ended up with too many rows per partition to be efficient. So we decided to create a surrogate key that combined 2 fields, the date and let's call it a product group, yeah, which was something that in our case had values from 1 to about 50. Yeah, and we made it 4 digits, so if the company ever goes crazy and instead of 50 product groups decides we need 3,000, we still have a way to putting it in. We would probably not be able to partition anymore, but right now this is what it is, and we just stitched the numbers together, so we did that. Not saying you have to do that. In our case, it helped us a lot to eliminate a lot, because we figured out all the queries that hit our data filter by year, month, and that group. Yeah? Pretty much every query that we ran against it. So that made sense. In your case, something else. Just keep an open mind and think, how can I slice it in the most common groups of data, because that helps you speed up. Let's imagine you have 3,000 partitions, and you can eliminate 2,999 of them every time you query. That sounds like a big gain, yeah? And I will give you a lot. Yeah. You have to speak up. I can't hear you. They are filtered in the where condition mostly. It could be, no, not in a join. Yeah, it has to come in the where condition. No. Still? No. The partition, so the question is there a sweet spot for a number of how many rows you put in one partition? That's completely independent. Yeah? So each partition has its own row groups. And each one of them should be the 1,048,576 rows. That doesn't change. Yeah? It's just, you basically have these little buckets, and now you're cutting the buckets into separate rooms kind of thing. You're putting some here, some there. Yeah? But how many of these buckets, row groups, are within one partition depends on how much data you have. There's no sweet spot. What I'm saying is don't put too much data into one partition because you have to scan too much. That's the only thing you can basically limit with your where clause super efficiently. Other things you can do better. So next thing, and this is the biggest one. Clustered Columnstore can deal with almost every data type that SQL Server has, at least in 2019. Before that, there were always restrictions. And the restrictions were there for actually good reason. Lifting them is, again, one of these features where Clustered Columnstore just says, yeah, I can do that. I'm not telling you that I'm going to be performing really horribly if you use that, but hey, I'll do it. So your new best friend, number 2, is a much simpler number to remember. It's 8 bytes. If your data fits in 8 bytes, which is equal to 64 bits, Columnstore loves your data and can process it super efficiently. If you use anything that's larger, Columnstore says, yeah, I'll deal with it, but I'm not going to even try to be good. Yeah? I'm going to store it. I'm going to compress it. But all my optimizations, I'm not going to use. Yeah? So which are these column types that you can actually use? Big int, float, int, binary 1 to 8, character 1 to 8, tiny int, small int, date time 2, time, money, small money, lots of money, date, more money. Lots of them, and probably a couple more. If you stick to these data types, a lot of magic will happen that we're going to discuss in the next couple of slides. Yeah? Thing is. So, as we said before, the data is somewhere on the disk in these individual rows, and row group by row group gets pulled in. But what if, when we put a where clause in there, and we're not even getting all the data back, we're just getting back the data that we need. So versus I have it on disk, and I pull it in memory, and then I filter. What if I could already filter when I read it from disk and never even bring it in? Yeah? So that's very different. So for example, you only like red M&Ms. What if you can buy the bag, and magically when you pull it out of the shelf, all the non-red ones disappear and get replaced by red ones? And you just bring home a bag of red M&Ms, and all the other colors stay behind. Yeah? And this is exactly what filter pushdown can do. So if your data type in a column that you filter on is 8 bytes or less, and your where clause is reasonable, and I cannot define what reasonable is. Yeah? But trust me, if you have 15 function calls, it's not reasonable. Yeah? If you have where equals something, greater something, smaller something, that sounds reasonable to me. Yeah? But I cannot define where the limit is, what they can do. It's not really published. Maybe Nico knows more about that. I don't know. Thing is, yeah? What I've seen is like betweens, greater than, smaller than, maybe one and condition in between, maybe one or condition works just fine. Thing is, reasonable. Yeah? If you put an where in and then a list of 3,000 parameters, that's not going to be reasonable. Yeah? Thing is, yeah? If you do that, SQL Server cleverly only brings the rows that match that condition into memory to begin with, so that the rest of the query processes only the data that actually meets that. Yeah? That puts the amount of data that needs to be shuffled around in memory down a lot, especially if you have like awesome queries that said like where processed, non-processed data, and like 99% of your data is already processed, and you just want the last percent or so, and you filter on that, you just get 1% of the data instead of 100% back on a query. So in a row store, it would have pull in every row, every column, even the ones we don't deal with, then apply the filter, and then work with the data. Yeah? In Columnstore, if it uses more than 8 bytes, it just pulls in the one column, but all the values, then applies the filter and moves on. In Columnstore, with less or equal 8 bytes, it tells the storage engine, give me all the values that match, and just that number comes back. That's a huge optimization. Yep.
Are you talking about the row group header elimination?
No, that's the next one. That's just filter push down. Yeah, doesn't matter. That works on every column. Thing is, we'll get there. Yeah. So the next one is lots of queries. I actually just want like an aggregate, a sum, an average, or something of the data. So instead of pulling in 1 million rows and then calculating the average, wouldn't it be awesome if the storage engine just could give me back the average instead of bothering me with the actual data? That's called aggregate pushdown. Everything that's less than 8 bytes, and again, the aggregate is reasonable. So if you put 15 functions that call each other in the aggregate function, it will not be pushed down. But if you do a sum, a min, a max or so, it will just haul back in the result and not all the individual rows. Yeah? Same thing as before. On a regular row store, has to pull it all in and then calculate the aggregate. Columnstore, more than 8 bytes, pulls just in the one row, calculates everything. If it's 8 or less, it just receives the result from the underlying storage engine, which is amazing from a performance gain. So, next one. That's what Andrew, yeah, there's a question. It's in the query plan. It says filter push down, aggregate push down, that's little remarks. Yeah, you see that in the thing. So the question was how you see it if that actually happens. And the other one is the little clock in the bottom, how long your query runs. That one too. Seconds suddenly become minutes if you change something, and then you know it's not happening anymore. So row group elimination. So we already talked about that you can wholly eliminate partitions. The whole partition goes away and doesn't even get looked at if your thing is. But Microsoft came up with another clever idea. You remember that little table that's underneath it? They found an extra 16 bytes there to stuck it in. So for every row group and every data type that's less than or equal 8 bytes, they store the minimum and maximum value that's in that row group. And when you look for certain values, instead of going through the whole list, uncompressing it, looking at it, storage engine churning through it, they just look at the metadata, basically, oh, is anything even possible in that piece? If not, they ignore it. Yeah? So let's go through that. So let's imagine you have one row group that has custom IDs 1, 3, 4, 5, and 6, and the second one has 8, 9, 10, 11, 12 up there. Yeah? And you do min and max values would be 1 and 6 for the first row group and 8 and 15 for the second one. Yeah? And then so on. So they have that. So if you run a query where custom ID equals 9, it will look at the first row group and says, 9's not between 1 and 6. Not processing it. There's no possibility it will ever be there. Just move on to the next one. Next one, oh, yeah, that's within. Let's process it. And then everyone after that, everything is. Yeah? Problem is, Columnstore by default has no order. You can't order it in any form. The way it basically keeps the data the way you insert it right now, but every time you rebuild the index, the order might change and everything else. Yeah? So you might have 10 row groups, all over the place that have values of 9 in it. Yeah? But as it's implemented right now, and that's pure implementation, and that might change in the future, columns like a date or ever-increasing numbers, yeah, you insert them basically in order, and within a row group that you insert, they stay there. Even if you rebuild it, they're not moving around massively. They might move one to the left, one to the right, but they're not moving all the way over. Yeah? And again, that's purely implementation. Yeah? Might change in the future. But if you're clever when inserting the rows, and you pre-sort them by things you filter a lot, you're not only helping the compression because you have the same values all over the place, you're also helping yourself a lot in queries with that row group elimination. So just imagine our 3,000 partition before. So we have the 3,000 partition. We didn't look at 2,999 of them. And now we have, let's say, 1,000 row groups in there. And we nicely sorted them by custom ID before we inserted them. And now we're looking for one customer, which is probably in 1 or 2 of these row groups now. We eliminated another 900 plus something at a time. So from a couple of 100 millions of row groups that there were out there, we're just down now to 100 that we actually have to process. That's a lot of gain. And for that, we used the pushdown on the aggregate pushdown, and the query finishes, and all the numbers at the bottom of SQL Management Studio still read 0. Yeah. Or a couple of seconds instead of several hours, just because we didn't pay attention to data sizes and used a var binary 9 to store a zip code because we felt like it. Yeah. So, next magic thing that can happen. So all this was just to build up to the real performance killer that makes it really much, much better. Yeah? Batch mode. Batch mode is something they came up with for Columnstore, and it turned out it's so great that they're now starting to implementing it for many other areas in SQL Server, because the thing is. So what is not batch mode? You all seen a query plan and all these nice little icons, yeah? And data gets literally passed on from one of these icons to the next one underneath. Yeah? So what happens is that the last icon on this side asks the one before it, like, hey, give me data. The next one says, hey, give me data. Hey, give me data. Till finally it's the one that actually pulls the data out of the database that says, yeah, here's one row. And then this one says, oh, I got a row. Here's a one row. And the next one says, here's one row. And then this one says, ah, great. It has the value 7. I remember that. Give me the next one. And then it works all the way down and then all the way up. Now you know why your queries take so long. That happens all the time. Yeah? In batch mode, all they did is said, the first guy says, hey, I need my data. Same thing down there. And the last guy says, hey, yeah, all the conditions are fine. Here is 936 rows. And the next guy says, great, taking it, moving it over, moving it over. So while walking up and down, instead of moving one row, they moved 936. Again, that's implementation as of right now. It's something around 900. Right now, most of the time, it's 936. And we will learn why. So processing almost 1,000 rows in one go instead of one by one, another big win in the whole thing. Only can happen if the rows are less or equal to 8 bytes. And this is why. Because some genius about 10 years ago that makes CPU chips came up with an idea. We're really like at the limits what we can squeeze out of these chips, but we can do more things in parallel. What if we create instructions that instead of working on one element of data, can work on 4 of them at the same time? Wouldn't it be great if we can process like 4 items with one instructions at the same time? And that's exactly what batch mode uses. And this is where the limits come in. And this is where all the limits come in we talked all the time before. Yeah? So modern CPUs can do single instruction, multiple data instructions. That means if I want to add up 2 values, I can do 4 of them at the same time. So this looks like this. So basically, each one of these lines in this diagram is one of our columns. And since they're 8 bytes, there's 64 bits. 4 times 64 bits is 256 bits. and that's the amount of data a modern CPU can process in one go. So if I want to add up these numbers, I can instruct the CPU to do it for all 4 rows at the same time in the same instruction while going through the data in one go. And if you take 64 kilobytes, divide it by 256 bits, and add some metadata overhead to it, you end up with the number 936 right now. If they need a little bit more or less metadata in the future, that number will change. Yeah? But basically, that's why it's about 900 rows at a time. Yeah? So this, not just that it works on 4 columns at the same time, it moves the data in 64 kilobytes at a time through the whole process, which is much faster than 1 column at a time. Yeah? So that's batch mode. It makes it a lot faster. So what happens data types that are larger than 8 bytes? Columnstore just operates them. It just doesn't use any of the features I talked in the last 15 minutes about. Very simple. It just ignores them. It can't do it, and it can't selectively just do it for 3 columns and then ignore the last one. The moment you have one in there, the thing is, you can still have them in the column store as long as it's not in the query. Yeah? So you can store an additional column that is bad. Just remember, if you include it in the query, so select stars, really bad. If you selectively just have it there, it works. Just if you want it in the query, try to ignore it. What we ended up doing is all the data that has basically long strings like computer names or anything else, product names, we put in a separate lookup table and then referenced it with an ID. Yeah, that's what we ended up doing. It's a little bit more overhead to create all that, slowly changing dimensions and all that. We noticed from 50 years of creating data warehouses, a little bit of overhead, but it was worth the query speed because practically we're not querying reports that need 3,000 different values. Most of our queries go in with, I need for this value all the facts. Yeah? So you look up the one value and then put it in the where clause where you need it. So archiving data. Columnstore has 2 modes, regular compression and archive compression. Archive compression just takes a little bit more time to get about 30% more compression, which then you pay every time you decompress. It takes longer to decompress. Thing is, we do it. We keep the last 2 or 3 weeks in regular compression and use archive compression on everything old. Just in the next maintenance window or so, we rebuild that one partition, the oldest one, and move it slightly to the archive, mostly to save space. Yeah? The query performance, yes, there are differences. You can measure them, but they are not worth the effort. But the space savings of 30%, when you have 15 terabytes of data, 30% is a lot. It's 5 terabytes. That's 5 terabytes I don't have to back up every day. That's 5 terabytes I don't have to pay a storage company to provide it to me. Yeah, archive compression. So the thing is, I wouldn't do it on the data that you're constantly still working with, because that costs you a little bit. There's a second type of archiving that we want to implement, but we're still fighting and try to figure out what it is. What we usually tell our developers is, hey, if you have old data that you're not using anymore, move it from your primary database to an archive database. With Columnstore, works just fine. Select from, into there, use through a linked server, whatever method you want to do is, use SSIS, whatever. Only problem here is, when you do that, the data gets uncompressed while you move it. Because you're retrieving the data, it uncompresses it all and then moves it on the other side. And that can become a little bit tricky. Yeah, because that can create a lot of data in between. I'm fighting with Microsoft to get them to copy the underlying rows, row group at a time. Never uncompress them, just move them to the other side and just magically fix the metadata and make it the table again. It should be possible, it's just they need motivation. So if you see any Microsoft employee, just stop them, yell at them for 20 minutes, and tell them to do that. You can tell them, I told you so. No, just kidding. Backups. backup compression surprisingly still can compress archived column stores. I can't explain why, but it still squeezes out another 30%. So, yep, I still, even if my database is 99% column store, I still use backup compression to back it up. It's still worth it. Saves you tape, disk space, cloud space, wherever you put your backups these days. So that's a good one. Yes. So, coming to the end, where are the limits? Simple. I don't know yet. I haven't hit it. I've hit many other limits. Here, I right now have about 1 trillion rows. That's that many zeros. I wish my bank account looked like this, but unfortunately not. That's about 15 terabyte in compressed form. The original table has 168 bytes of data in it, all less than 8 bytes apiece. So that gives us about a 1 to 32 compression, or 5.5 bytes on an average row. So I take 168 bytes and make them 5.5 bytes in Columnstore. That's insanely awesome. But also, if you try to export that data to anything else, it just explodes. It's several petabytes of, did I do the math? Yeah, it's about half a petabyte of data just in 15 terabytes. Yeah? And just imagine, backup can squeeze another 30% out of that. So it's mind-blowing how good compression came of these days. And the talk I mentioned with Bob Ward, he explains 2 or 3 of the 10 different algorithms they use to compress. It's amazing. Yes, yeah. So where are the limits, part 2? Yes? Backup deduping? No, I don't think so. When you use compression with backup, you're not getting any kind of dedupe on the underlying storage.
No, I'm just saying, just back up the column store with deduping like the combo.
As I said, if you compress any data, you're not getting any kind of dedupe. And also, my personal opinion, dedupes are not backups. If you dedupe your data on your backups, you only have one backup of your data. If anything fails, all your backups are gone in one go. So I would not recommend that. But again, yes. So in our query, 3 trillion rows, most of our queries that we run can be done in less than 10 minutes. Most of them are like a minute or 2 that we run against that thing beast. Yeah? And again, that's on a commodity server that costs about $50,000. So nothing super special, just regular box that your favorite hardware vendor can supply. So we're doing count stars, we're doing sums, average, mins, max, all kinds of what you can think of. We're retrieving regular rows. We're doing distincts in them. So all kind of this. So this is mostly handled by aggregate pushdown that we discussed before. Then we do always a where date and our product group kind of thing. We always do that. That's column A in our case, date and A. That's always in the where clause. That's handling the partition elimination. So that gets rid of like 99% of the data before we even get there. Sometimes you have to query a whole month or 2 months or 3 months. Then less elimination, but still there. Yeah? And then we normally have one more column that we filter on. That's one of the columns we pre-sort the data before we insert it in. So we get awesome row group elimination on the next column. So we have 3 columns, date, A, and B, that we basically can eliminate all the data in one go if we don't want it there. Yeah, so that helps with row group elimination. And then we do C, and that's more filter push down. Yeah, any other column, C, D, E, F, G, is just filter push down, gets us the data quickly out. Then we do a couple of group bys, and there's one more bracket that makes no sense there. Please ignore. And that's, again, handled by the aggregate pushdown. It can also do group bys for you. Yeah? So, yes. And the whole thing, most of the time, we can write the queries in a way that it runs in batch mode. So this is, if you're really take care of your Columnstore index. You fill it in perfectly, and you limit all your data types to what Columnstore likes. All this can work on the same thing again. And out of billions of trillions of rows that need to be processed, you're suddenly down to a couple of millions. And that goes like this. And you have your results. Yeah? If someone 10 years ago, 10 years, 5 years ago has told me I can run a query against 3 trillion rows and get a result in 10 minutes, no. Because even with the best indexes or whatever at the time, that seemed to be impossible. But nowadays, not a big deal. So that's a talk. We have about 10 minutes left for Q&A. So yes.
You mentioned that for Columnstore, you actually use its own disk.
I use it, so the question is,
How do you do that in Azure?
okay. So the question is, I specified that I use my own file group and how you do this in Azure SQL database. And I don't know, but my money would be as you can't. I don't know. I don't use the cloud. Sorry. And my guess is not, because you have no control over the underlying file system structure. So I would be surprised if they let you create another file group there. So if anybody knows, yeah.
Can you share your experience about which column you will pick up for the column index, or just the?
Yeah. So the question is, if I can share my experience, which one I use for the column index? None. Clustered Columnstore doesn't have any kind of index key. It's the worst name for a product I've ever seen. It's not an index. Clustered Columnstore index is not an index. It should only be Clustered Columnstore, but unfortunately, it's called Clustered Columnstore index. It's not. It never had. It's not. It was an index when you put it on top of a regular table at the very beginning, but if it's its own table, there's no index. There's no clustered index key.
I think I need to change my question.
Yeah.
Which column you pick up for the column store?
So
When you create that column, you store it.
the column store index, the clustered column store index, is all the columns of your table. You cannot choose and pick. If you convert your regular table to a clustered column store, it contains all the rows that are, and all the columns that are in the original table. So you have to clean up the table before to make that. I mean, you can create an empty clustered column store table as well. Thing is, yeah, which probably the columns I pick for the partition elimination and all that, the ones I filter the most on. I don't care about the actual data in it. Yeah? If it comes up in a lot of queries, it's a candidate for optimizing for. It's very simple. Yeah? It's not the data that defines it, it's how the data is used. Yes?
So if I have like a 10 billion record table,
Yep.
and it has like 30 or 40 columns, which one of them happens to be XML.
Yep.
Instead of trying to convert that to column store, would I just pick out like the 3 columns that I think are most meaningful and put them in a whole nother table as column store, and then like link back to them to
So-
get the rest of the data?
So the question is, if I have like a medium wide table, roughly 30 columns, and one of them is XML. Yeah, the beast. How should I deal with it? And again, it depends massively. It was a couple of billion rows. And I'm guessing the XML is very different in each row. Yeah. So 2 options that I was asked which one is better. You could separate it in an external table and reference it, but that would have every column in it. Yeah? If you're in 2019 and you convert your XML into text, you can actually store it inside the column store, and it will compress it and try its best. But the moment you include it in your select statement, all the optimizations are out of the window. On the other hand, if you run your statement with all your optimizations and then you have to join to another table, you are also creating some extra work for SQL Server. So I couldn't say without actually testing both versions. which with 20 billion rows is not a fun thing to do, but still in the realm of possibility, or you pick like a sample of 100 million or so and make both versions and then see which one performs better. Again, in 2019 you can do it. In anything before 2019 you can't do it because the data type couldn't be that big. And it would not be able to store all the XMLs, assuming they're not just a couple of bytes, they're like real documents. So that, yeah, I would try both. Columnstore is good at compressing, but it's not good at compressing like raw text. It can do it, but that's not what it's optimized. It's optimized to compress numbers. In the end, text is numbers, so it might end up doing a great job, but keep in mind, if you include it in the select, you can do it. Yeah? Before 2019, it's very simple. You have to put it in a separate table. Starting with 2019, you have a new option. I'm not sure if it's a good one. I haven't had the case there. Yes?
Is there any scenario where you would put a non-clustered index on top of the clustered column store? And does it have any impact
Yeah.
on any of the stuff?
So we tried that on this table for one column, one big int number, and we ended up, so we have 15 terabytes of compressed column store, and the one secondary index for one 8-byte column was 16 terabytes in size. Yep. It worked when we wanted exactly one row with that number. We got it back like this. The problem is, every time we inserted, we basically created twice as much data as we needed to. So we dropped it. Yeah. Could there be a case where it makes sense? For sure. But my guess is if it's a smaller one and you don't care so much about doubling your data, so if you only have like a gigabyte or two of data and you're adding another gigabyte, that's not a big deal. If you have 15 terabytes and you add another 15 terabytes, that becomes a big deal. Yeah?
Yeah, we have some tables that are relatively small, 50, 60 billion rows.
Yeah.
And they look up single rows, so that it works well there.
Yeah.
But on the larger ones, we found that the adding a single non-cluster index slowed down the update process so much.
Yeah.
It wasn't even the size.
Yeah.
It just slowed it down too much.
Yeah. So to repeat what Andrew said, he has smaller tables with double, triple digits of million rows. It works great there. On the big ones, their processing slowed down massively because of the overhead of maintaining that. Yeah. So, yes, in the far back.
On this 3 trillion row table, have you done any other joins in any tables?
Yes. So the question is, on this table, are we joining? Yes, we're joining with 6 other tables. Almost every query joins with all 6 of them. That are regular row store tables that have the value we join on is the primary key that is it's a regular column store, not column store, sorry, a regular clustered index on the external table. So we basically created a very simple snowflake kind of thing where we operate in, star schema kind of thing. Very simple. That works just fine. What we've tested, and we said, ooh, that ends up very badly. If you have like 2 of these 3 trillion rows or billion row tables and you join them, that's really bad. Yeah? Because that needs to be an hash match join thingy, and that creates basically a copy of your data in TempDB. And with the compression ratios, that goes really, really bad very quickly. So we figured out we had to limit it to like 1 hour of data to actually successfully join it. And we had about 8 terabytes of TempDB. So you can imagine if you have like billions of rows and try to put that in there, that hash thing blows up just. But one column store to many other regular tables works just fine. 2 column stores with each other join, not a happy couple. Yes? Yes. So the 8-byte limit also works with fixed size strings. Yes. Yeah. If you can keep it to 8 bytes, it's great. Yeah. For SQL Server underneath, these 8 bytes are 8 bytes. Doesn't care if it's a string, a number. It's a binary object that they store for. Yeah. There, all the way over there.
If you were doing index rebuilds on Clustered Columstore, do you need to max dot restrict that down?
Yeah, so the question is, if we do index rebuilds on Columnstore, yes, we restrict the max stop to one, same thing. I just don't want to risk it. I assume that Microsoft could be clever and do it wisely, but I've been disappointed before, so I'm not. Thing is,
I've seen situations where clients are running massive
Yeah.
boxes. I'm talking 40, 60 cores,
Yeah.
stuff like that, and you'll end up with 40 or 60
yeah,
really close row groups because it's just whatever's left over on each core
yeah. So that.
when you rebuild.
Yeah, so this max up one, what I would do if I have that beefy box to do that, I would maybe run multiple processes and each one does one partition. So I create my own max stop. Yep, so rebuilding the indexes with max stop greater than 1 might mess up your row group assignment because it will break it up, especially if you have strange max stop numbers that are like odd, like max stop 3 or 7 or something, whatever your DBA feels like. That might mess up. And even if you specify max stop 8, that just means that's the maximum you're allowing. SQL Server then still can choose to only use 5 and completely mess up your whatever you're doing. Yeah. So in this case, max stop 1, a good friend.
Reorg single-threaded too.
Yeah. Yeah. No. Yes.
How does this work with sparse columns, or is it just not a good idea?
Question is, how does this work with sparse columns? Honest answer, I don't know. I've never used a sparse column in my life. I'm not SharePoint. Sorry. I see use cases. I never came across one where it made sense. Nullable columns, very careful. If your column is nullable and it's like a big int, that's 8.01 bytes. Yeah, so if you have a nullable column in there, keep it at 7 bytes. Because otherwise it's more than 8. The nullable bit is 1 extra bit that comes into the 8-byte calculation. Thank you for bringing that up indirectly. Good. Yes, one more here.
Question on a row store table that has a non-clustered column-store index on it, and it includes all the columns. Do I have any performance difference between a query that hits that table versus the same table that's just simply built on a clustered column store?
Probably not. So the question is, if you have a regular table and you put a column store secondary index on top of it versus you just have the whole thing. I don't think so. I honestly don't know if they implemented all the optimizations we've pushed on or so on the secondary one. My guess is yes, but I'm not 100% sure. You still have the overhead of maintaining the regular table all the time when you add new data. But you might gain a lot because some queries are really good against Columnstore, other ones are really good against row store. Yeah? So just as one more reminder, if all your queries are to find a single row, Columnstore is not helping you. Columnstore is helping you, I need to look at the whole thing and find something out of the whole thing. This is where Columnstore is good. Yeah? If you need like group by date and you have 10 years of data, this is where Columnstore really becomes powerful. Yeah? If you need that one row, yeah, you're reading it all and finding the one row. You might have all the optimizations that we can put in, but again, any regular table is going to be much more efficient at that. And I don't want to sound like a broken record. It depends. Like, they should rename the product instead of SQL Server. Just call it "It Depends." Yeah. Yes. Varchar 8 works just fine. Sorry, Varchar 6. Varchar 8 is 10 bytes. Unless you only put 6 bytes in. You can still define it, but not use it. But that's very tricky because then people tend to forget that and put 10 in or whatever. So Varchar 6 is the limit. And I think I put that correctly in the slide. If not, I will correct it. But it's 2 extra bytes at the beginning that unfortunately count. Yes. Yeah. More questions? Yes. Yeah. Yes. So the question is partition maintenance functions like switching, merging, splitting. Yes. So we try to avoid splitting because that's heavy. but we do a lot of switching in and out. This is how we actually maintained the index before 2019, when there was no online index rebuild. We just took a partition out, and like the data has disappeared. We maintained the partition and then put it back in, so we didn't block the table with the index update. Or if we need to delete or something, we pull it out, do all the work, clean it up, and then put it back in. Also, when we put it into the archive compression, same thing. We pull it out, re-archive it, pull it back in. We merge when we go to the final archive server, because there we have the partitions are larger. So we drop the product ID in the past, because in the archive, in the primary system, we keep 2 years of data where we can have these 50 extra groups we put it in. In the archive, where we want to keep like 10, 15 years of data, we can't afford to have that many partitions. So we have a different partition scheme in the archive than we have in the hot data table. Yes, more questions? Yes, there's one more.
Will you show that slide again that had the data types that were okay?
Sure, I try. Maybe I use the mouse. Here we go. Yeah, I didn't put varchar there because it didn't make sense to me, but it should work with varchar 6. So we can add that. And the slides are already uploaded to the PASS website, so they're all available there. Thing is, thank you very much. Please fill out the eval forms. A little shameless plug, I have another session on Friday talking about cloud or not to cloud. That's the question.